Okay, so we're on chapter 3, where we want to introduce another new sequence, but it's a very natural step forward from what we have. Previously, in the arithmetic sequence concept, for example, we had something like, maybe let's start with a 2, maybe a 5, 8, 11, 14, that kind of sequence. Why is that an arithmetic sequence? Arithmetic. Because the difference is the same. I'm adding the same number, in this case a 3, every time. Now, I could have also subtracted something. It would still be an arithmetic sequence. When we instead multiply by the same number every time, we'll call that a geometric sequence. For example, I could decide I want to multiply by 3. Then 2 becomes a 6. Multiply by 3 to get 18. Multiply by 3 to get
24.
18 times 3.
Oh, 18.
Good practice. 54. Did you use your calculator? Don't use your calculator. It's good practice. No, you're not, sorry. So, even though I'm starting with the same number, I'm still using a 3, the result is not at all the same. And the multiplication sequences grow much faster. So, let's write this down. A geometric sequence with, we still need to know the first term. Could be a 2, but it doesn't have to be, right? So we'll call that A again. And in the arithmetic sequence, I needed to refer to this difference. We're not going to call it the difference now, the number we multiply by. We're going to call it the ratio. Could be a 3, but in general we'll call it R. Is a sequence, I'll just say it informally. It's totally fine. Where we multiply each term by, each consecutive term by the same number, R. So if we first just translate this with a recursive formula, our example, well, we're not doing arithmetic now, so let's cover that up. Our example says start with term 2, then to get a term in another position, take the previous one and multiply it by 3. So the recursive formula is not complicated. It looks very similar. We're just multiplying instead of adding. And that gives us a totally different sequence, so it needs a new name. In general, I won't know what the first term is, so I'll just call it A. And the rule for how to get from one to the next is still the same, but I'm not multiplying necessarily by a 3 like our example. I'll multiply by some number R. That number still has to be the same though. So in your explanation of a geometric sequence, you can use a specific example. You can leave it general with the A and the R. It's totally up to you. But page 4 of the quiz will be to explain what a geometric sequence is and give the formulas, just like page 2 is for arithmetic sequences. It'll be page 4, and it'll be geometric sequence. Okay? But we have one more kind of formula, right? We haven't done the explicit formula. Everyone happy so far? Ooh, the sun's out. Wow, that's nice. Take it while we can. For the explicit formula, I'll use my example, 2, 6, 18, 54, and just try and see what is the pattern here. So I'll do this on the side since it's not necessary. I just want to convince myself. So we had position 1 was the number 2, position 2 had the number 6, position 3 had the number 18, position 4 had a 54, and if we keep going, well, maybe do one more. Position 5 would be the 54 times 3, which would be 162. And then we can keep going, but that should be enough. Okay, so we're going to do the same thing, trying to pull this number apart and see what is the calculation really. So the 6 is the previous 2 times 3. The 18 is the previous 6 times 3, but 6 itself is, oops, not 6, 2 times 3 from before. And then I have another 3 to multiply by. 54 is 18 times 3. The 18 in detail is 2 times 3 times 3. And then I have a new times 3. And 162 is 54 times 3. 54 itself is 2 times 3 times 3 times 3, and the new times 3. So it looks very similar, except it's now multiplication. We did the same thing for the arithmetic sequences, trying to find the explicit formula. A table like this is so handy to find explicit formulas. But we don't have to. Once we're sure, we can just remember it. So let me put all these below each other. So I have 2 times 3, sure. The third one, I have 2 3s, so that's 3 squared. Then I have 3 3s multiplied together, that's 3 cubed. Then I have 4 of them together, will make 3 to the power of 4, and so on. So now I see that the actual calculations hiding behind these terms are where the 2 is always there. That first term is always there. It's always a number of 3's that I multiply together. The only thing that's changing is how many 3's. So what is the link between the position and the number of 3's I multiply?
One less.
It's 1 less again. But because it's multiplication, it appears in the exponent. So that gets me to a formula where if I want to find the term in position n, it's 2 times a number of 3's, and the number of 3's is 1 less. So there is my explicit formula specific to our example. We can then say, okay, well, the 2 is the first term, the 3 is the ratio, so that means in general, it'll be an equal to a times r to the n minus 1. So let us zoom out and see something like that. So again, page 4 of the quiz is, well, not the bottom, but this part. There it is. You can explain what a geometric sequence is with an example specifically or not. You need a sentence to explain what it is, and then the 2 kinds of formulas. Same thing that we did for page 2, the arithmetic sequence. Any thoughts or questions so far? Easy enough. It's a new explicit formula to memorize. Yeah. But it's not a very long one. And also, and still, just like for the arithmetic sequences, the key properties, the key numbers in the sequence feature in the formula. The first term and the ratio that I multiply by. No thoughts? Too easy?
So the fundamental differences are the multiplication.
The only difference. Yeah. And because that results in a different sequence, the formula looks slightly different, everything is slightly different. Now, you may ask or wonder, okay, well, we did some interesting questions for the arithmetic sequence, so can we do it for the geometric sequence as well? And the first one was, I have space. No, I don't have space. Making it up. First kind of question, exercise 3.2, is here's a random formula. Does this formula describe a geometric sequence or not? Exercise 3.2. So my first formula is an 2 times n squared. So perhaps I'm going to memorize my geometric formula, my geometric sequence, explicit formula, in exactly the way I wrote it. Sometimes, even if it does describe a geometric sequence, I don't recognize the formula. I can always just make the first few terms of the sequence, 5, 3, 5, and see what is the pattern. Does it fit the geometric sequence? So in this case, the first term is position 1, term is 2, at 2. Second term, n is a 2, 2 times 2 is 4, times another 2 is 8. Third one, 18. Do I need to do more? Why is it 18? How do I get 18?
3 times 3 is 9.
The n is 3, so 3 squared is 9, times 2 is 18. Now I'm trying to find if this is a geometric sequence specifically, right? So in order to look at multiplication, I'm going to multiply by 4. It's the only way to go from 2 to 8 in the geometric sense. And the next multiplication is not 4. That means it's not a geometric sequence. And I move on with my life. To be a geometric sequence, I have to multiply by the same number every time. And if it's not the same every time, there's something else I'm not interested in right now. Yeah.
So we only know what the n is because they gave us, like they said, n equals 1.
N is always the position. So whatever position I want to pull in, that's the n I'm used to calculate. Let's look at something else. This formula is 4 dot 2 to the power of n. That dot is multiplication. But again, it doesn't look exactly like the explicit formula I memorized, so I'm not 100% sure perhaps. Let's be sure by making the first few terms in the sequence. So position 1 will give me 8. Position 2, 16. Position 3, 4 times 8, yes. You're right, 32. So I'm starting to feel good. Yeah, this is multiplying by 2 every time. So far, it's not enough evidence to really make me feel very comfortable. A couple more. N is 4. 2 to the 4 is times 4.
64.
64. And that's again a times 2, yes.
Why wouldn't 1 be 4? Because if you're
The whole calculation. So n, this is n,
Mhm.
right? So then that means the first term is 4 times 2 to the power of 1.
Oh, I see.
That's it.
Okay, in the previous exercise, I just was like, oh, 2 is A, and A is the
Oh, no,
first
no,
term,
no,
so
no.
that's, okay.
Actually, yeah, if I, in my simple formula for an arithmetic sequence and a geometric sequence, the first term is in that formula.
Right.
Other formulas, no, it's not going to work.
Okay.
Could be anything.
Okay.
I can't say, oh, I see a 2, so therefore, no, I don't know. Could be anything. One more. Position 5. Is it 128? So I multiply by 2 every time. So this is a geometric sequence with first term 8 and ratio 2. Then the question asks, if it is a geometric sequence, find the other kind of formula. The given formula at the top there is what type of formula? Explicit. So I need to state the recursive formula for this sequence. That starts with telling me what the first term is, 8, and then telling me how to get the term in position n, whatever, take the previous one and multiply it by 2. Together, that is the recursive formula. And we start seeing these things over and over. Yeah, slightly different multiplication this time. Last time it was maybe addition, little variation. But the kinds of formulas and things like that we should be getting more used to now compared to day one. It was a little overwhelming for me. Any thoughts? Yeah.
So the equation at the top is explicit because you're not given the first term.
It's explicit because the only thing used in the calculation, the right-hand side, is the position. It doesn't ask to look at a previous term or anything. It's just what is the position, calculate, and that's your number.
And whereas recursive, you
Recursive says to find the term in any position, you have to look at previous ones.
okay.
That's the difference.
So are we going to be asked to write them in both forms in the quiz?
For page 2 and 4, where you explain the arithmetic sequence and the geometric sequence respectively, you have to give both. For page 1, I give you one, you just have to use it. That formula could be explicit or recursive, and it could be anything. And then question 1b is those 4 basic ones, powers of 2, powers of 3, and so on. So those are all explicit. So there's not much formulas you have to come up with. That's brand new. This is really just getting me used. This question is not exactly a quiz question. It's just getting me used to the geometric sequence. One more. A1 is 2, and an is 3an minus 1. Now, if you compare that to our recursive formula, it does look similar. The multiplication, the 3 is just put in front, but perhaps you're not sure. You have to still read this recursive formula saying first term is 2. This is exactly saying multiply by 3 every time. And that is exactly what the geometric sequence is doing. So I don't really see the need to make the whole sequence because the question doesn't ask for it. It just asks, is it geometric or not? And based on the recursive formula, so directly explaining what we are doing from one term to the next, in this case it's multiplication, and it's always a 3, therefore it is a geometric sequence. But you're welcome to fill in the rest of the sequence if you want to. So this is a geometric sequence. It was a little less obvious when the explicit formula was given, but the recursive formula is essentially instructions for what to do, and those instructions match exactly what the geometric sequence instructions would be. So I have first term 2 and ratio 3. And then this was a recursive formula, so I need to find or say what the explicit formula is. I memorized that as an equals first term times ratio to the power of n minus 1. You can put brackets around it, but BEDMAS tells you the exponent comes first, then the 2 is multiplied.
What does the A represent?
The term in that position. Yeah. The subscript is the position. So this week, really our goal is to just sort of fine-tune the quiz questions and our understanding of those questions. Getting used to things that keep repeating. They repeat for a reason. They're the most important things. Any questions on that exercise 3.2? Yes.
So when you said like sentence,
Yeah.
each time you do that, do we all also have to write what the formula is?
No, the question is asking really two things here. The question is asking, determine if it's a geometric sequence, and then I always say, if it's a geometric sequence, I attach first term ratio. It's one thing. And then the second part of the question says, write the other kind of formula.
Okay, so if it didn't say that.
I wouldn't write everything. I would just say, geometric sequence is first term 2, ratio 3. There were two parts of the question. I mean, you're welcome to. And there's no harm in thinking that you should, because on page 4 you have to anyway. So if you write more than you need to, it's okay. Just make sure it's correct. Now,
I have a question.
oh yeah, sorry.
Okay. So where it says n equals 2, 3, 4, are you just starting with like position 1 would actually be like I'm thinking
Position 1 is not listed in the second circled part of the ratio equation because it's given separately.
Okay.
For recursive formula, because it says that the one that's circled there says, take the previous term and multiply it by 3.
Yeah.
If I want to use that circle part to find the first term, I need to look back to a previous term. But there is no previous term. So I can't do it for the first term. That's why the first term is given separately. Because only from the second, third, and so on can I look back. Which is why the second part says the general AN portion of the recursive formula only applies to position 2, 3, 4. Because for that portion, I need to look back. So I need to be in at least position 2 to be able to have something to look back to. If I stand on position 1, I look back into the void, there's nothing. I can't use it. So the drawback, if you want to think of it like that, for a recursive formula is it needs to set up the beginning so that I can start my loop a little bit later. Different.
Those, so with the geometric formula for both recursive and explicit, it's not the exact same as what we're.
No, when they give me in that question, they're trying to trick me by making the formula look a little different.
Okay.
And then I have to figure out, is that still a geometric sequence? It might not be exactly the formula that I memorized, but it could just be a simplified version or something. Otherwise, if they give it to me exactly the way I memorized it, there's no real challenge. It matches perfectly. They're trying to be tricky.
What about when there's a zero? One of the problems there was a zero.
Yes, that is a typo that is unfortunate. Did I?
That one's sneaky. I was like,
I'm sorry.
okay. You can tell us.
To make it simpler for us, in general, those things have more variety. To make it simpler for us, our position is always going to be 1, 2, 3, 4.
Okay.
Typos aside.
But for this one, it has to be.
My sequence starts still at position 1.
Yeah.
The loop just can't start with position 1. The loop has to start a little further because it keeps going back. So I have to make sure there is something to go back.
Got it.
Yes. All right. Now there is, I don't know if it's good or bad news. You decide. If we think about the problems we did for the arithmetic sequences, we had something like space. I don't have space. Right. We had something like exercise. Let me go back and say exactly which one. 2.2. Exercise 2.2, where the sequence was given and it asked how many terms are there in the sequence. So let's remember exercise 2.2. It was how many are in, what was it, 1, 5, 9, 13. Where did I stop?
125.
125. Okay. How did I do that?
Explicit formula.
Yes, but how do I know what explicit formula to use? Right. Because I'm always adding, I identify this as an arithmetic sequence first, which then leads me to the appropriate explicit formula, 1 plus n minus 1 times the difference 4. And then, now I have the explicit formula to use. How did I use it?
See, time was it? It's not times 4, isn't it? Just
It's always times 4.
Okay.
That's why it required a little memorization. How did I use that formula?
Solves for n.
I plug in the 125, or this way, the end one, and then and then I'm trying to find the value of n, which will be the position, which counts them exactly the way I want. Okay. It helps to remember these because we're going to talk about the same kind of problem. Okay. Now, in exercise 3.3, we have again a how many kind of question, and my sequence is 1, 5, 25, 125, and it keeps going, and it hits 9, 7, 6, 5, 6, 2, 5. That's still one number. The reason this gets so big so fast, not because there are that many terms, but it's because I'm multiplying every time. Making that what kind of sequence? Geometric sequence. So notice how we're following the same strategy, right? Geometric sequence, which has a formula. Now eventually you will memorize it, fine. It is the first term times the ratio to the n minus 1. Because the sequence is different, the formula is different. So I have to use an appropriate formula. And these are the two that we memorized. So we won't get questions outside of them. But notice now it's the same strategy. Which means next I'm going to plug in this quite unpleasant big number and look for the corresponding position, right? Strategy is the same, just a different sequence, so a different formula. Still looking, whoops, not n. Still looking to find the corresponding value of n. But compare the two equations that we get. Previously, we got an equation, and we had the basic algebra tool to solve that top one. That was totally fine, I hope. The bottom equation is not the same kind of equation because of where the unknown sits. The n is in what I call the exponent level. Making it a very different exponential equation. And the bad news is that even though our sequence didn't change that much, we just made multiplication. Multiplication is not that complicated to understand either. We end up with an equation that is not as straightforward to solve. And it requires some maybe pre-calculus concepts that we of course don't have and we aren't that interested in. So for our purposes, this is a little bit too fancy, we'll call it. It's not difficult if you have the tools. Why? I will. If I give you this question, too fancy is an acceptable answer. Too fancy to solve for us. I'm not saying you can't. I'm saying it's a little bit, grade 12 is a little bit far from our goal, right? So sad face. But with a simple enough question on this topic, we have always, it's not a very flexible strategy, but a first strategy is always a guess and check strategy. It's always there. It's not something I want to rely on too often, but it's always there. Which means I could try some values of n in this equation and see if I get the target number I'm looking for. So maybe let's try n equal to 8. That means I then calculate 1 times 5 to the 8 minus 1. That'll just be 5 to the 7. And see, how close do I get? Maybe I'm very close, maybe I'm not even close. I have no idea, right? So I have that as a backup, but it has limited uses. I can use it here. It's going to be okay. What do I get if I try an 8 for the answer, n? Then my calculation on the right-hand side of that equation simplifies to 5 to the 7. Calculator says 5 to the 7 is 1.
78,125.
So that is a little small. Right, my target is in the millions. That's a little small. Okay, so next one. What else could I try?
32.
No, he said 32. Let's try 32. 1 is... That's the downside of guess and check. You jump around and it could never work.
But eventually the window closes.
Eventually the window closes, exactly. So what does your calculator say for 5 to the 31? Is it doable?
It just, I don't really know how to read that out.
Okay, so we'll just make
I'm a little high.
so it's a little big, Calculator space. Okay, so I overshot it.
Yeah.
Try 10. 10 might be a more reasonable.
So close.
5 to the 10. Remember, the minus 1 is required in the calculation, so that gives me 5 to the 9. How close is that? Of course, I know all my powers are 5, but I want you to do it.
1 million something.
1 million something. Can we be a little more specific?
Okay, 1,953,125.
Just in case someone wants to check. So I'm close. So maybe one step, one more, maybe 11. I don't want to jump too far because I'm so close. So 1 times 5 to the 11 minus 1 equals 5 to the power of 10, and you'll see that is correct. So it's a strategy that obviously is a little more tedious. I'm just jumping around, trying numbers, hoping to sort of get close. It's not something I can rely on for too long, but because this is a little bit beyond our level, it feels okay that we can still at least find the answer. We don't really know much more. To solve exponential equations, you need something called logarithms, and they're a little bit more towards calculus, a little fancy for us. But it's interesting for me to see that just changing the arithmetic sequence idea to multiplication, which isn't that fancy, and I get things that are suddenly much more complicated in their formula, and that's in the same kind of questions suddenly become a little bit unpleasant. So if you're curious, when I wrote the book, I thought I'm going to show it to them, but in hindsight, I think it's more off-putting than enlightening. So it's there if you want to read it. I'm happy to explain it all to you, but we don't need to know it.
Please remember to click the like button if you enjoyed the video, and to subscribe if you want to be notified of more videos. Thank you.